So you guys are going to have your notes out. You guys are going to copy this in while I come around to check that little homework page to see if you did it or if you tried it. Okay? I'm not looking for much, so just deal with whatever you got and start copying this in, okay? On the front side of that packet. Okay, so hopefully that was enough time. If not, you can keep copying while I'm talking, okay? So what we've got here is just, it should feel like a review. It should not be too much new information. Cation and anion might be like not too much there, but that's okay. But what I want you guys to notice is that for your metals, we call them cations when they have more of a positive charge, okay? What does it mean they did with their electrons if they became more positive? They got rid of an electron. So your metals tend to get rid of electrons, okay? And we're going to hopefully keep that in your mind as you look at your trends today, okay? An easy way to remember that cations are positive is they have that little T right there, okay? Your metals tend to be your solids, the exception being mercury at room temperature. And then group 1 and 2 are reactive. Hopefully today I'll be able to show you guys the little YouTube video showing group 1 in water, and it's kind of cool. If not today, it'll be on Thursday, I promise. All right, nonmetals. Nonmetals are on the right-hand side of that metalloid stair step, okay? And we call them anions when they become an ion, okay? And they become more negative. So what does that tell you? What did they do with electrons? They gained electrons. Exactly. Nice work. So, and the easy way to remember that they're negative is the little n right there, telling you negative. Anions are negative, cations are positive, okay? And that tells you what they did with electrons. All right, your nonmetals tend to be your gases, and your halogens are in group what? Oh my goodness. It is not group 7, y'all. 17. 7A is fine, but 7 is not okay. All right. So they have 7 valence electrons, but they're in group 17. Remember, it goes all the way across to 18. You guys have to have that one memorized, y'all. What's group 1 called? Alkali metals. What is group 2? Alkaline earth. What's all that middle group called? Transition. And what's group 18? What's group 16? Oxygen family. Good. All right, good. Okay, cool. All right. And then finally, your metalloids. So metalloids, the ones that are along that little stair step, these guys have properties of both your metals and nonmetals. They tend to be your solids, or they tend to be solids. But I put a positive, negative thing there because these guys can sometimes swing both ways, right? So they can either gain electrons or they can lose them. A lot of them are in that group 14, meaning they have 4. So they could easily lose 4 as well as gain 4, okay? So that's where that kind of came from. All right, so do you guys have any questions over properties and things like that? We're all good? Sweet. Okay, so your homework. This I gave you guys yesterday, okay? I gave you this little information here yesterday. So just a reminder of what we talked about. Coulomb's law is all about that attraction between positive and negative things. What was the little analogy I told you guys to think of, or the visual to think of? Magnets, exactly, all right? So, and especially for this first one, the first model, where it's talking about your distance. If you hold magnets really close, they're going to try and connect. If you hold them really far away, they're not really attracting each other as much, or you at least don't feel that force. Okay, so as you increase distance, you're going to decrease force. We saw for model 2 that as we moved down the family, that force got smaller. So as you move down a group on the periodic table, the force to those electrons is getting smaller. They're not being held as tightly. That's going to be very important today. Very, 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 very important. Are we all clear on how important it is? Okay, super important. Glad you asked. All right. Model 3. Model 3 was about your number of protons and attractive force. So we talked about how your model here was showing you that we were increasing your number of protons, okay, in the nucleus, obviously. And how is that affecting that attraction to the electrons that are floating around in the outside? Well, as we increase those protons, we're going to increase that force, okay? Because what you can kind of imagine is those 4 protons for one of the electrons on the outside. And it has that 4 proton to 1 for each of the electrons on the outside. This is super important today. Super, 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 super important today. Are we all clear on how important it is? Super. Glad you asked. All right. And then finally, Model 4 talked about across the period. That was where we saw that as atomic number increases, we know atomic number from 8-man is your number of what? All the time. Every single time, atomic number is your number of protons. Okay? Who is it most of the time? Also, electrons. However, we know that electrons get tossed around like, you know, for ions, right? And we know neutrons are never guaranteed because those are isotopes. But protons are your atomic number. So as atomic number gets bigger, you got more protons. You got more attractive force to the nucleus, okay? And then finally, this last part we didn't really talk about in class, but it's showing you that what I just told you is those protons, when you have a number of protons in that middle, it has that same force to each individual electron. And that's why as your atomic number gets bigger, it's pulling in on those electrons very, very strongly. We're going to see how that affects things like radius, ionization energy, all that good stuff today. Okay, so you guys are going to do a little hunting in just a few. All right, and then you also need to remember those electrons are repelling each other. Okay, and that helps keep them a little organized. And I think that's it from this. Okay, all right. Let's look at those answers to your homework. If you did your homework, cool, then all you have to do is check them. If you did not, you're copying like a mad person. Okay, and I'm running through it fast because we need time to do our exploring today. All right, so number 1. Okay, number 1, assuming that Q1 and Q2 remain constant, what will happen to the magnitude of your force? All right, just so we're aware, by the way, this is Coulomb's law right there. Right, that's Coulomb's law. The V, when you get to physics, turns into an F. Okay, so all that it's talking about is the force between 2 charges over a given distance. That little K is a constant. It's Coulomb's constant. Don't worry about that right now. All right, and then number 1 was saying if you keep those charges constant but you move them further away, that's the magnet analogy. Your force is going to decrease. And then this is just setting you up for what those the things in the equation are. So if Q for a proton is a positive 1, I'm sorry, if an electron is a negative 1, Q for a proton would be positive 1, neutron would be 0. Something for carbon, whose atomic number is 6, means that the nucleus is going to have that positive 6. That's where that number came from. For Model 1, the first one, would you expect to observe attraction or repulsion between subatomic particles? I interpreted this as your protons and electrons, so I said attraction. Okay. And then what is the dependent variable in the data? I gave you that answer yesterday. No excuses. No excuses. Okay, and that was force. All right, so we increased distance. Force did something because of that. All right, the next part, Model 2. Okay. What do the arrows represent? And they represented your force. The thickness represented the amount. Using a periodic table, locate those things. They were in the same group or column. And we noticed that as we moved down the column, that force decreased. Please keep that trend in your head. Super important. All right, over here. Model 3, what are the independent and dependent variables of the data? Independent was your amount of charge, your positive charge or your number of protons. And then the dependent was your force. So as we increased charge, positive charge, you increased force. So it was a direct relationship. Model 4 was using periodic table to locate them in locate the elements. They were across the same period. And the 3 that had out of the 3, chlorine had the strongest, the one who was mostly to the right, the one who becomes an anion because it likes its electrons, all right? Cool? Keep that in mind today. All right, and then finally the last one, so it was just saying that each electron gets the same amount of force. So as I have a bunch of protons in the middle, each one gets that a bunch of proton attraction. That's all that this is trying to get you to see. And then finally, the two that are repelling, electrons, the ones that are attracting are your electrons and protons. Okay? So Coulomb's law, big deal today. Our objective up on the board is telling us that you guys are going to recognize your trends today. And it tells you that you guys got to be ready to turn around and explain to me, why is that trend occurring? You're going to relate it to this Coulomb's law homework, so use this page a little bit when you start talking about why. You're going to use words like shielding effect and effective nuclear charge. Quick question, what do you think shielding effect is? Out of the distance one, or do you think it's the proton one? It's the distance one. As you put more energy levels, you get fatter and fatter and fatter, right? Okay. And effective nuclear charge. What is the word nuclear charge telling you? The protons in the nucleus, okay? So those are your two arguments. Everything is related to Coulomb's law. I just want you guys to see that, okay? So please use this page today when you go to explain why. All right. What you're going to do now is you're going to turn to your whiteboards, the marker, the eraser, and that little packet that says class set. You can close your notes for now. On your desk, what you have is you have a packet full of a bunch of these, okay? And they all have different periodic tables showing different numbers on it. You're going to work with a partner for the next 8 minutes, okay? And you're going to analyze each of these charts, and you're going to write down your observation on your whiteboard. The sentence stem that I think you guys are going to be using or should be using, I have to give this to you because I first period it got a little lost on them a little bit what exactly I was asking. So what you're saying is across a period, blank either increases or decreases, okay? Down a group, blank increases or decreases, and you're going to pick one or the other, okay? That's really what you're doing. You don't have to write the whole sentence if you don't want to, but that's what you guys are trying to do. Each one of these periodic tables has a different title. Look at the titles and use that for those blanks, okay? Now, one more key. Each of them also has one of these, which I know looks like every periodic table that you've looked at, but they're different. This is showing you that bottom number is your atomic radius. On this one, it's showing you that the bottom number is your ionization energy. On the next one, it's showing you that it's your electronegativity, okay? So pay attention on each one that you're looking at, what exactly you're looking at, okay? I would use the numbers more than the pictures, okay? But the pictures of the radius will help you as well, okay? All right, so I will leave this up here, give you 8 minutes. You can work with a partner. Try and get all the trends written down on your board. There are 5, okay? Save electron affinity for last. When we looked at atomic radius, what did we notice about your numbers going across? They did what? They decreased. Good. So across a period, you should have had decrease. Down a group, they increase. Okay? We're going to write all this on a summary page soon, so it's just checking your answers right now. Okay? Real quick, though, let's talk about the why. Okay? Who can... Yes. No, not quite, because they actually become more, to be honest. All right, so as you move down a group, why do they get bigger and bigger and bigger and bigger and bigger? Not quite that. Not quite that one. You said what? They get more shells, you guys, right? Don't they? As we increase in energy level, what happens? You get a new one, you get a new S orbital, right? And then you move down another energy level, you get a bigger S orbital. You move down another one, you get a bigger S orbital. All right? Do you guys see that? So they kind of are making layers. All right? So as we move down, we have that. And we know as you move down, what happens to that force of attraction? As you move bigger and bigger and bigger, it decreases. No, it way decreases, right? So those electrons, so those electrons are kind of loose and really like not even being held very much, all right? All right, as we move across, though, we get smaller. Why? It's one of your Coulomb's law things. So why do we get smaller going across? Here's your hint.
Because there's more protons.
More protons, exactly, all right? So as I increase the number of protons inside that nucleus, they start grabbing all those electrons. They're like, haha, I have 9 now. Haha, I have 10 now. And they just like squeeze them in really, 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 really close. Lots of attraction. Think of magnets sticking together, okay? All right. So the next one you had was Ionic Radius, which is a weird one. If I can get it on here. There we go. All right. So first of all, who's your cations? Who tends to be your cations, you guys? Metals or nonmetals? Metals. Good. So everything to the left of your metalloids line. Who tends to be your anions? Nonmetals. Good. So everything to the right. And that's actually where this trend breaks into two pieces, is right here on this little stair step right here. Okay? If you look at everything to the left of the stair step, you see a trend. What is that trend as I go across the period? Is it getting smaller or bigger? It gets smaller, so we're decreasing. Okay? As I move down a group, am I increasing or decreasing? I'm getting bigger, so I'm increasing. Okay? Again, on the right-hand side of this metalloids line, do we see that it is doing the same exact thing? Yes. So your ionic radius trend is the same as your atomic radius trend. So no matter what, those same two rules that we just talked about apply. Okay? However, one thing that I hope you kind of looked at was I want you to see what's francium's atomic radius. Or I mean ionic radius. 180. Okay, let's look up here. What is carbon's? 260, right? So what I need you guys to see is anions are always fatter than your cations. Okay? Anions are fatter than your cations. Reason why? Actually, I want you to tell me the reason why. What did the anions do? How did they become negative? What did they do? They gained electrons. What are those electrons doing to each other? Repelling. So basically, they're like going on with their happy life, and then they get a little electron in there, and they poof out because they're like, I ain't going to be eaten by you. All right, so they get really, 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 really big. So all of your anions are huge. Your cations, on the other hand, what did they do to one of their electrons? They tossed it, right? They're like, there you go. It's gone. So now I have more protons than I do electrons. They squeeze in tight. Cations are small. Anions are big. Okay? Now, you don't have to write that down right now. We'll deal with that again probably Thursday. Okay? But can you guys see that the trend was still the same? It still gets smaller across, bigger going down. Okay? All right. Cool. How many of you guys made that observation, by the way, the metalloids line? No? All right. Well, good. Hopefully you see it now. Okay? All right. What was next? This one? Your electronegativity? So electronegativity, what did we notice going across on electronegativity? We got bigger, yep. And what did we do going down a group? Smaller, we decreased. Good, okay? So why? Why is fluorine have this huge, oh, I'm sorry. Let me tell you what electronegativity is. Electronegativity is how they bond with each other. So what I like to think of, and I put it on the same page as electron affinity. Electron affinity in my, the way I usually describe it is a love of electrons, how much they want those electrons. So we're saying fluorine has huge electronegativity when it goes to bond. Why? How far away is it? How far away is it from a noble gas, y'all? Yeah, just shout it.
So the more valence electron spots are filled at the outer shell, the more electronegative.
True story, because it is so close to becoming a noble gas. Yes, yes. Okay, so so fluorine just needs one electron, and it's already super small, which means it's really attracted to those electrons, all right? So huge love of electrons. However, francium, poor electrons on francium. Francium like forgets about its electrons. Do you guys see that big difference there? 4 to a 0.7, not even 1. Like francium's like, take it, all right? So, so those are the two main, I hope you're seeing that we're looking at two main corners here, okay? And that's the way to remember your trends, all right? Electron affinity, I threw this one on here because it is related to electronegativity. I don't need you to memorize this one, but I did want to point out something that's kind of cool. Do you notice all of these are zeros? And do you notice, it kind of breaks down here, so don't worry about these guys. But do you notice that manganese is a 0, zinc is a 0, and all of your noble gases are zeros? Okay, if I told you, don't answer this, but why? What is important about all those three things? I want you to think of electron configuration. What is this group 2? If we were to write it, it would be like 2s2, right? 2s2. They're filled, exactly. This one looks like this, right? What does it look like when you get to manganese? All the bunk beds are filled, right? When you get to zinc, then it's filled totally. So it's your orbitals being used up, okay? So that's what I wanted you guys to see. And you kind of see it with nitrogen too, and it breaks down again as you get lower. Everything breaks down on the periodic table. It's great. But I wanted you guys to see that on electron affinity. However, the overall trend is that within each one of those things, you're getting smaller, okay? Sorry, you're getting bigger on the negativity scale, okay? All right, keep doing that. What's the last one? Okay, cool. Ionization energy is how easy is it to pluck away a little electron? Okay, so who can you tell me is holding on to their electrons super tight? Fluorine or francium? Fluorine is. Fluorine is not going to let you pluck an electron. You have to use so much energy, and it is very evident right there. Even further, look at your noble gases. Are they giving anything away? No. They're like, heck no. And helium on top of that, who has them like right next to their nucleus, heck no, you're not going to take an electron away. Yeah, that's why, yeah. That's special stuff there. All right. And then as you look at francium, he doesn't even show up. It's like, he's like, please, he like has like a for free sign on the side of the road. He's like, please, here's all my electrons right here, right? So francium does not require much energy, if any, to take one away, okay? So we saw that hopefully ionization energy has the same trend as electronegativity, and that is that as you move across, you what? You increase, and as you move down, you decrease. All right, cool. So now you guys are going to write it on your summary page, okay? Ooh, not what I meant to do. In your packet, your notes packet. Okay, we're going to write this quickly, and then we are pretty much almost done. Okay, so your trends on your periodic table, aside from Coulomb's law, kind of are based off of that all atoms want to have how many electrons? How many electrons does every atom out there want? 8. So put 8 on there. It's kind of based off of that as well, okay? So that love of electrons and all that good stuff, okay? All right, your atomic radius is your size of your atom, okay? And we said that going across, you are decreasing or increasing? Remember, you're decreasing. Fluorine is tiny, so we're going to put a little itty-bitty S in this corner. I'm sorry, don't put it outside helium. Put it by the fluorine. Noble gases kind of have their own, like, little bit there, too. All right, so fluorine, super, super, super small. Francium, super, super, super big. Okay? So as you move across, you decrease. And as you go down, you are increasing. Good. And off on the side, I want you to say, no, nothing off on the side yet. We'll come back to that. All right, for ionic radius, okay, this is the size of common ions, okay? I want you to put your little metalloid squiggly right there. It doesn't have to be perfect, I don't care. Okay, but within this, remember, you have a small corner and a big corner. Here you have a small corner and a big corner. Okay, so it still follows the same trend. You're going to decrease across to that metalloids line. You're going to increase going down. So kind of your group one, no matter what, kind of works out, but the period one stops at the metalloids line and starts over. Okay, so remember, carbon is huge. That's the biggest one on here.
Good morning, Rand. Please stand for the Pledge of Allegiance and the moment.
You guys all copied this down? Yes? Okay, and we'll talk about it more on Thursday. But just so you know, there's work on, it looks like this. So it's not the next couple pages, but the next couple pages have all the information that I've kind of been blabbing at you. Thank you. But this page you can kind of start looking at. These are not multiple choice questions. You're saying which one is bigger, this one or this one. Okay, and only do the ones that you know we've talked about. There's a few that we haven't talked about yet. So, but try a couple of them, and that way you're keeping up. Otherwise, sleep tonight for your test tomorrow. It'll be fun.